In continuation with our earlier discussion, we are going to discuss few more terminologies, and today we'll be focusing upon very important concept, and that is performance evaluation. So let's have a recap what we discussed in the last session. So we had a discussion related to the size of hypothesis, and we mentioned that it is possible that the size of hypothesis space is too big, right? And it is really very difficult. If I am having many number of hypotheses, those are possible for a given data set, then it would be very difficult to evaluate or to check each and every hypothesis for its performance and for its suitability for the given problem. And that is why what we need to do is we need to come up with some hypothesis space which is limited in its size. And to do that, we have actually gone through the concept of inductive bias, right? So we mentioned that choosing appropriate hypothesis space requires some kinds of assumptions, and the assumptions made to make a hypothesis easier to learn and to limit our hypothesis space, we have introduced this term that is inductive bias. Also, we have gone through two kinds of biases, restriction bias and preference bias, right? So, we know what is restriction bias and we know what is preference bias. Under restriction bias, we specify the form of the function that we would like to use to limit our hypothesis space. And in preference bias, we put a condition, we put the assumption like what kinds of functions we are going to prefer out of whatever is the space, hypothesis space that is defined, right? We have seen the examples as well for these kinds of biases. After that, we have a discussion regarding the consistent hypothesis and the generalized hypothesis. So we said that a hypothesis is said to be consistent if it agrees with all training examples. And we mentioned another concept, and that is generalized hypothesis. So we say that a hypothesis is said to generalize well if it correctly predicts the value of y, that is my output, for unknown sample, right? So this is what we have discussed in our last session. So today we are going to continue with one really very important concept related to hypothesis, and that is fitting the hypothesis. So you might have aware of this term, fitting a function, right? You might have studied this in statistics. So in statistics, a fit refers to how well you approximate a target function. I repeat, in statistics, this word fit refers to how well you approximate a target function. In machine learning also, we are using this terminology, fitting the function, because supervised machine learning algorithms seek to approximate the unknown underlying mapping function for the output variables given some kind of input data. I'll repeat. In machine learning, supervised machine learning algorithms need to approximate unknown underlying mapping function, we say that it is a hypothesis for the output variables given some input variables. So given some training data, using supervised learning algorithms, what we actually trying to do, we are trying to come up with a mapping function that maps my input with output, right? And these mapping functions are nothing but the hypothesis, and that is why as we are going to come up with such kinds of mapping functions with respect to machine learning algorithms, this concept of fitting the hypothesis is most appropriate, and that is why we are going to discuss what we mean by this fitting the hypothesis. In fact, right now I'm just going to introduce you the concept. We are not going into the details. Whenever we go for learning various kinds of algorithms, I'll be focusing more upon these concepts. But this is just for your information and understanding the concept. So let us assume that we are having this data. So all these three figures are having similar kind of data if you look at these samples, right? Now, if I'm having this kind of training data available with me, so let me once again remind you that here x1 and x2 are the two features. Those are describing the observations in my training data set, right? So we are having here the samples, those belong to two different classes, right? And these samples are described with two features, x1 and x2. Am I clear? Yes?
Yes, ma'am.
Yes.
Okay. So this is what the data that we have. Now, what we are going to do next is, we are going to use some kind of supervised learning algorithm now, right? To come up with the hypothesis, to come up with the function that maps my input with output, right? So here output is the class label. I am having circle class, I am having this cross, that is another class. So I may say that I am having class 1, that is circle, and this red class, it is class 2. Okay, so I want to come up with a function now that will classify, that will distinguish this data in two classes. Okay, so I may have this kind of a line, linear function, right? And if I draw this kind of a line, it is possible for me to distinguish this data to some extent. Okay, so this is one of the hypotheses that I may have. I may come up with such kind of a function. It is also possible to come up with such kind of a function, and this function is also enabling me to distinguish the samples, those belong to two different classes, right? Now, in the third situation, I may come up with such kind of a function also. This is a very non-linear function. I may come up with such kind of a function as well, right? So all these three kinds of functions we may have. Okay, now if I'm having such kinds of functions, then I need to look at which mapping function or which hypothesis suits me the best or suits our data the best, right? Or what is the right fit, what is the good fit for my data. So with respect to this, we are having now these three functions, say for example, and I'm going to tell you how to categorize these functions with respect to its ability to fit with the training data, right? So if we look at this first category or the first figure, we say that this is underfitting. You might have heard this word. These words are popularly being used while describing the hypothesis or learning algorithms with respect to the given data, right? So we may say that if we come up with such kind of a line for this given data set, I may say that this is underfitting. So what we mean by this underfitting? A statistical model or a machine learning algorithm is said to have underfitting when it cannot capture the underlying trend of data. It cannot capture the underlying trend of data. I'll repeat. A statistical model or a machine learning algorithm is said to have underfitting when it cannot capture the underlying trend of data. So let me give you one simple example. What is underfitting? And usually we use this kind of a word whenever we go for buying some clothes, right? It's just like trying to fit the undersized outfits. I'll repeat. It is similar concept that we are going to buy some clothes and we are trying to fit the undersized outfits. So if this is the case, then we say that it is underfitting. Okay. So similarly, if my machine learning algorithm is not able to capture the underlying trend of data for the given training data, then I will say that this particular hypothesis is not fitting well. It is underfitting because it is not able to capture the trend of the data, right? So it would be possible for me to come up with low accuracy for my model, right? So it may happen that we may come across, if I'm having such kind of a hypothesis that is not fitting my data well, and if it is underfitting, then it destroys the accuracy of our machine learning model, right? When it happens, usually it happens when we are having less number of samples, right, in our training data set. So if we are not having enough data in our training data set, right, also if we are trying to come up with a linear model, and if actually the underlying data is non-linear in nature, then also we may face this problem of underfitting. Right now we are not going to discuss further how to overcome this problem and all, right? I just want to let you know what is underfitting, right? So I hope you must have understood the concept. I'll repeat. Underfitting is actually considered as a problem in machine learning when the machine learning algorithm is not able to capture the underlying trend of data, and it reduces the accuracy of my model, right? Just I mentioned the reason maybe I'm saying maybe the reason maybe we are having small amount of data, right? And that comprises my training set, and it may also happen that we are selecting incorrect kind of function and we are trying to fit that function for different kind of data. So if I am having non-linear data and if I am trying to fit a linear function, then it may happen that this linear function may not be suitable for that kind of a data, right? So this concept is known as underfitting. I hope you must have understood this. If you have any doubts, please let me know. Yes, any doubts? May I proceed?
Yes, ma'am.
Yes, ma'am.
Okay. Now let us look at the next category, and that is overfitting of the data. Overfitting. My function is overfitting. So what we mean by that? Let me define this word overfitting. A statistical model is said to be overfitted when we train the model with lot of data. I'll repeat. A statistical model or a machine learning algorithm is said to be overfitted if we are trying to train our model with huge amount of data. And if I am having lots of data items, then there is a possibility that my data includes some kind of noise or some kind of exceptions. And if I am making use of such kind of noisy data, then what will happen? Then actually my model tries to learn those incorrect samples also. And if my model is trying to learn those incorrect samples, it may happen that it may come up with the function something like that for the training data set. So if you look at this function, it is really very consistent with whatever is my training data. So every sample in my training data is being correctly classified by making use of such kind of a non-linear function, right? But sometimes what happens is, due to huge amount of data present in my training data set and due to some noisy samples, my model is learned very much out of those noisy samples, incorrect samples, and it may happen that my model gives me such kind of a function that is very appropriate for the training data set, but not necessarily my real data that I am going to test is of such kind, and in that case it may happen that I will not be getting the correct result. Right? So this is what the concept of overfitting. So we may relate this concept of overfitting just like fitting ourselves in oversized outfits. Right? So the similar concept. I am having two big training data set including some incorrect samples or including some noisy data, and my model is trying to accommodate that noisy data as well, right? And it comes up with something like this, very non-linear function. And in fact, whenever we present a new unknown sample to such a model, then it may happen that the unknown data sample is incorrectly classified. So this concept is known as overfitting. So overfitting or under overfitting, our training data fits very well, right? But there may be the problem of generalization of my hypothesis. Okay? Now, I hope you must have understood this concept of overfitting also. And we do not want that our model is either underfitting the data or overfitting the data. But what we expect is a good fit or a right fit. Okay, so whatever you look at here at the middle, that is actually the right fitting, we may say. Okay, so what we mean by this right fitting? Right fitting is ideal or it is a kind of expected model or expected hypothesis that we may have, right? So ideally, when the model makes prediction with zero error, we say that it is a right fit or it is a good fit. Okay, so if you look at this function that we have drawn here, right, this function is actually able to separate out these two kinds of samples from one another, right? But in training data, if we look at this, I don't say that this function that we have come up with is consistent with my training data. But it may happen that this is the generalized function. This is the generalized function, and it may provide me the good accuracy for my model, right? It may happen ideally that my model makes prediction with zero error. And if this is the case, then that kind of a hypothesis is the good fit, or it is a right fit. Right? So we have gone through three important concepts: underfitting, right fitting, and overfitting. Okay, we are not going into the details right now, but this is just for information. Just I wanted you to know what we mean by underfitting the hypothesis, overfitting the hypothesis, and what is a good fitting of hypothesis. If you have any doubts, please let me know. Yes. Any doubts?
No, ma'am.
Whether the points are clear?
Yes.
Let's look at few comments, final comments regarding the hypothesis and hypothesis space. So usually this task of concept learning is a task of searching an hypothesis space of possible representations, looking at the hypothesis that best fits the data given some kind of a bias. So we are having huge hypothesis usually, right? So we impose some kinds of biases with some assumptions, and then this task of learning becomes simply the task of searching an hypothesis space for a best fit, right? Searching the hypothesis space means out of the limited hypothesis space now, finding out the most suitable hypothesis, the most suitable representation that fits best for the given data and for the given bias, right? So the tendency to prefer one hypothesis over another is actually called as a bias. And we are having a classical example of inductive bias, and that is known as the Occam's razor. So what this Occam's razor is, it says that the simplest consistent hypothesis about the target function is actually the best. So out of many different kinds of hypotheses, those are possible. It is usually the best hypothesis that is of the simplest form. So the simplest consistent hypothesis usually proves to be the best one, and that is what the Occam's razor says. So it is not always necessary to come up with some complex function or some complex hypothesis as a model for learning the data, but it usually suffices that we come up with a simplest consistent hypothesis, and actually that fits our data well. Okay, so that is what the Occam's razor says. Some more examples of inductive bias, just I am quoting here. We are not going into the details of any such inductive bias right now. We may have the minimum risk. Yes.
What is that Occam's razor?
It is just one concept. It is just one guideline. So what kind of hypothesis are actually suitable for a kind of data? It is just a guideline proposed by that Occam, and that is why it is called as Occam's razor. So Occam's razor is just a guideline, And this guideline says that usually we need not go for more complex hypothesis functions, but it is really possible that come up with the simplest consistent hypothesis, and that is a best suitable one. So this is just the guideline that has been provided, right?
Okay, ma'am.
Fine. So I'm having here few more examples of inductive bias. As I mentioned, we are not going into the details of any of these biases right now, but this is just for your information. We may have minimum description length, right, for our hypothesis. We may have maximum margin hypothesis, right? And that is one more kind of inductive bias that we may have. Right now you may not understand these concepts, and that is why I'm not at all going to focus upon this. Maximum margin hypothesis is being used with respect to SVM. So whenever we go for discussing SVM, at that instance, I'm going to explain you the concept. Right now, this is just for your information that there are certain guidelines to pick the best hypothesis, right? And please remember, it is not always the case that the hypothesis is really very complex function. Sometimes it may happen that we come up with a very simplest consistent hypothesis, and that suits our data very well, right? So we need to always think of something that is very simple, okay? If required, depending on the complexity of underlying data, we may think of having something complex, right? So I hope you must have understood now all these terminologies. And now we are going to discuss about the performance evaluation, the concept of performance evaluation, right? So what we mean by performance evaluation? In fact, if we are doing anything, any task is being performed, right? To find out the effectiveness of whatever is the task performed, we actually need to evaluate the performance, right, after performing the task. Say for example, if you are learning something, you are learning machine learning, or you are learning any of the courses, right? How to assess the performance, what you have learned? Obviously, what needs to be done is there should be some mechanism to evaluate your knowledge or to assess yourself, right? And that is nothing but performance evaluation. So whatever is the performance you show for some unknown questions based on your earlier knowledge, your learning. Based on that, actually, the teacher or we are going to assess you, right? So you are learning. So you are right now in supervised learning mode, let us assume, because you are being supervised by some teacher for various courses, and you are undergoing this process of supervised learning. So you are learning lots of concepts, right? You are gaining the experience, you are gaining the expertise in the subject, right? But after that, to what extent you have learned, right? That needs to be evaluated. So how this evaluation is done? You might be asked some questions, might be those are not seen before. So what you need to do? You need to apply your knowledge and you need to solve these questions. That is what we call as exam. So whatever is asked in the exam, you are supposed to write the answers. You are supposed to provide the solutions for the problems. Those are being asked in your exam. right? And you are going to write those answers based on whatever knowledge you have acquired earlier, right? So after writing those answers, ultimately you will be getting your score. So how correctly you have solved the questions based on the knowledge that you have, and that is what we call as performance evaluation, the assessment, right? Similarly, in machine learning also we are having the training data. We are coming up with some hypothesis based on that data, right? So what next? How good that hypothesis is, how good my target function is, that is what I need to assess. And this is what we mean by performance evaluation in terms of machine learning algorithms, right? So we are having few performance measures, right? Those are actually based upon some experimental evaluation, right? So what kinds of performance measures we may have? We may compute the error with respect to my learning algorithm and the model or the hypothesis that I have created. What next? I may find out the accuracy of my hypothesis. I may find out the performance in terms of precision, recall, and so on. We are going to look at all those terms, what we mean by that. Okay? Also, while performing the experiments, right, we need to follow certain sampling methods. And what are those sampling methods? We may have the train set, by making use of which actually we are going to train our model, right? We may have the validation data set, making use of which we are going to find out intermediate results, and we may iterate through. We may come up with the most suitable model, and for that we make use of the validation data set that validates whatever is the model that we have built. And if it is not appropriate, we just go on tuning the parameters of our learning algorithm, and once again we try to learn and validate. So this is the iterative process. So once it is done, we present our algorithm some test samples. And if my algorithm is predicting the test samples correctly, then based on that, it is possible for us to find out or to evaluate the performance of our model. Okay. Also, sometimes we may use the k-fold cross-validation mechanism as the sampling method. So we are going to focus upon all this, right, in this section of our discussion. So let us proceed now with evaluating the predictions. So if I want to evaluate my hypothesis, how well it is predicting my unknown data, then we are going to have some mathematical expression to evaluate our target functions, right? So let us assume that after building a model, okay, we are going to present a new example x to our hypothesis or a target function. I'm repeating the thing. So what we are having now the model. Okay. So what I mean by this model, this is actually the hypothesis that I have created, h of x. It is a function of x. What is x? X is my input. Based on this input or training data, I have come up with this hypothesis h, right? So I'm ready with my hypothesis. I'm ready with my function. So what next? Once my model is ready with me, what I'm going to do next? I'm going to present some unknown sample x, and my model should predict the output for this unknown sample x. Am I clear? Yes.
Yes,
Are you
ma'am.
getting me?
Yes.
Yes, ma'am.
Okay. So we are having our hypothesis ready with us, denoted here as h of x. And now, once we are having our model created, we are going to present the new sample and we are predicting now the output y. Okay, so usually what happens is, whatever is my unknown data x, I try to substitute that in my function h of x, and this function will provide me the output. Okay, so let us assume here that y is the actual output and y hat is the predicted output. What I mean, I am presenting x as the input now, right? So actual expected output is y and my model is predicting this y hat. Are you getting me?
Yes, ma'am.
Fine. Now, how now the error is being measured? So what I am having now, x is my sample, x is my example. The output, actual output I know that should be y. The actual output should be the y. And whatever is my target function or whatever is my hypothesis, that hypothesis is producing the output as y hat. And now, if I am having now these two values with me, y is the actual correct value and y hat is the predicted value. Now, based on these two values, I am going to find out the error. Okay, so how am I going to compute the error? We are having several ways to compute this error. So let me give you the very first way how we can compute the error. Okay, this kind of error computation is known as absolute error. Absolute error. So how we are going to compute this error? See here how we are going to compute it. We are having the difference, absolute difference between the predicted value y hat and the actual output y. Right? So what we have? We are having the absolute difference between the predicted value, that is y hat. So what is actually y hat? Y hat is nothing but the output that is provided by this hypothesis h of x. Okay, x is my input. So h of x is computing something, predicting something. So what it is predicting? It is predicting this value y hat. And I know the actual output, that is y. Okay, for my training samples. So how I'm going to compute the error? I'm going to compute the error like I'll be finding out the absolute difference between the predicted output and the actual output. So if I'm having n number of samples, n number of observations, then what I'll do? I will sum up all those differences. So this is actually giving me the error. Error for one sample, y hat minus y, error for one sample. So if I am having n number of samples, I will find out, I'll aggregate that error. I'll find out the summation of that error, right? And finally, what I'm going to do is, I'm going to find out the average error. Okay, and that is what we describe as the absolute error. Okay, any doubt? What this n is? N is the number of samples or number of examples that we have. Any doubt so far?
Ma'am, why we are
Yes.
taking average?
See, if I am having 100 samples, na, we are having 100 samples, let us assume. So, for every sample, I'll be computing the error. Right? So, if I accumulate
Yes.
that error, then it would be a big number maybe, and that may not reflect the real scenario. And that is why whatever is the error associated with every sample, I'll be summing up all those errors and then I'll be finding out the average of that. And that will be actually the good measure to compute the performance of my model. And that is the absolute error. And what we expect is that error should be minimum. Right? So it may happen sometimes. So what we mean by this performance evaluation? Let us assume that I am having H1x, that is the hypothesis 1. I may have another hypothesis, say H2x. I may have one more hypothesis, H3x, and so on. So what we are going to do next is, for every hypothesis, whatever is my data available with me, for every hypothesis, I am going to compute this error. And whichever hypothesis is giving me the minimum error, I'm going to pick that hypothesis because that is producing the minimum error. Are you getting me?
Yes, ma'am.
Fine. So this is one way of finding out or computing the error with respect to the samples that we may have. Another performance metric for computing the error is popularly known as the sum of square errors. Sum of square error. So what we typically do here is only one difference. In the earlier metric, what we did, we had the absolute difference between the predicted output and the actual output. Here what we are trying to do is, we are having here the difference, squared difference of predicted output and the actual output. Once again, this is the error, squared error. Okay, and for every sample, whatever may be my squared error, I am having the summation of all those errors, and once again we are trying to come up with the average error. Okay, and this is also treated as one more performance metric, sum of squared error. Right? And usually these performance metrics are useful for regression problems. I'll repeat, these kinds of computations for errors are useful for regression problems. We are having different metrics for classification problems. Whatever we discussed right now, computation of error in terms of absolute error and sum of squared error. So these two metrics are more meaningful and useful for regression problems. So what we do in regression we are having some data like this and we try to fit a hypothesis, right? So we may come up with such kind of a hypothesis, and what we next we are going to do, suppose this is my sample, right? So I am having some feature value x, right? And on y-axis, let us assume that I am having the prediction, actual prediction. This is actual y, and I am having this x, that is the input, right? But if I am having this hypothesis, then my predicted value is actually different based on this hypothesis. And what is that predicted value? See here, for this x, this line will provide me this y hat. Right? So this is my predicted value and this is my actual value. So I'll be finding out the difference in y hat and y. And for every sample, right, I will be finding out this error. And based on this error, it is possible either to come up with absolute error or the sum of squared error. And that will provide me a good way to evaluate my hypothesis. So this is one hypothesis. I may say, I may come up with one more hypothesis. Let us assume this line, or I may have this line, whatever may be the hypothesis. So for every hypothesis, I'll be computing the error, and whichever hypothesis is giving me the smallest error, that would be a best fit for my data. And typically these error computations are meaningful for such kind of a regression problem, wherein our y and y hat are the continuous values. Those are not the class labels, but these are actually the real values, continuous values, right? And it is possible for us to find out the difference between those values to come up with the error, right? So is there any doubt? Yes?
No, ma'am.
Have you understood the concept?
Yes, ma'am.
Okay. Anybody else who have any kind of difficulty, who have not understood the concept? These are really very important concepts. And whenever we go for building our algorithms or coming up with the models, we need to evaluate our hypothesis by making use of such kinds of functionalities to evaluate the performance of our model. So it is really very important. You should know this very well. Yes, any difficulty, any doubt, please let me know. Okay. So I'll just introducing you one more concept related to the performance evaluation with respect to the classification task. Okay, so we talked about the regression task, and for regression problems we'll be making use of two performance metrics usually, and that is the absolute error or the sum of squared error. Okay, now if my task is classification task, then I may have the performance metric like accuracy, error rate, and there are few more other metrics. Those are derived from whatever we call that as confusion matrix. So for classification task, we are having accuracy, we are having error rate, and also we are having few other metrics like precision, recall, right? Then the false positive rate, false negative rate, and many specificity, sensitivity. So these are the performance metric. Those are derived from one simple matrix known as the confusion matrix, right? So in the next session, we are going to focus upon all these different metrics. Those can be used to evaluate the performance of a classifier, right? So we are going to conclude this session today, and in the next session we are going to focus upon the performance metrics for the classifiers, right? And those are used, or those are derived from one important concept known as confusion matrix. Okay, any doubt? If you have any doubt, please let me know. Otherwise we are going to conclude this session. Any doubts?
No, ma'am.
Okay, so let's conclude this session. I'll be posting the link for the quiz. So all of you should respond to the quiz. Thank you very much.